Alright, let's dive into the concept of the circular queue. Actually, it's an extension of the regular queue, but with a twist. The last element is cleverly connected to the first element, creating a circular-like structure. Now, you might wonder, why do we need this circular queue? Well, it solves a significant limitation of the normal queue. In a regular queue, after some insertions and deletions, we end up with non-usable empty spaces, and that's not very efficient. But fear not, the circular queue comes to the rescue. By connecting the last element back to the first one, we eliminate those pesky non-usable empty spaces. And guess what? This means that we can use index 0 and 1 again without having to reset the entire queue by deleting all the elements. Isn't that neat? So, thanks to this clever circular structure, we can make the most out of our queue and it becomes a much more versatile and memory efficient data structure. So, whether you are managing data in a computer program or designing cool games, the circular queue has got your back. So, how does actually this circular queue works? Great question. Let's understand how the circular queue works and what is this circular increment means. Imagine we have a circular queue with 5 positions numbered from 0 to 4. When we insert elements into the queue, we move the rear pointer to the next position to accommodate the new element. However, there's a special trick when the rear pointer reaches the end of the queue, position 4 in our case. Instead of causing an overflow error and stopping there, the circular queue cleverly wraps around to the beginning of the queue, position 0. It's like completing a circle, right? So this process of wrapping around is called circular increment. So let's see it in action with an example. Suppose our circular queue is empty and we want to insert an element at the rear position, which is initially at index 0. We insert an element at index 0 and rear becomes 1. We insert another element at index 1 and rear becomes 2. We insert one more element at index 2 and rear becomes 3. We insert yet another element at index 3 and rear becomes 4. Now, if we try to insert an element at index 4, the rear pointer would normally become 5. But remember, this is a circular queue. Instead of causing an overflow error, the rear pointer wraps around and becomes 0. So the circular queue creates this circular motion, ensuring we can keep adding elements without wasting any space, making it much more efficient. And all of this is done using simple modular division with the size of the queue. Isn't that a clever way to make the most out of our data structure, isn't it? So circular queues are pretty smart and they come in handy when we need to optimize memory usage. Alright, let's explore how the circular queue works. Think of it as a special type of queue with some clever features. In a circular queue, we use 2 pointers to keep track of the elements. The front pointer points to the first element of the queue, which is the element we will remove when we dequeue. The rear pointer points to the last element of the queue, which is where we will insert new elements when we enqueue. Now, here is the fascinating part. When the rear pointer reaches the end of the queue, instead of causing an error, it wraps around and starts again from the beginning. It's like going in a circle, hence the name circular queue. To make sure our pointers are ready to go, we initially set both front and rear pointers to -1. This signals that our circular queue is empty and has no elements. With these pointers in place, we can efficiently insert and remove elements from our circular queue, making it a powerful tool for various applications. NQ operation. First, we need to check if the queue is full before adding a new element. We don't want to overflow it, right? So, when we insert the first element to the circular queue, we set the value of front to 0. It's like marking the starting point. Next, when we add a new element, we do something really cool. We circularly increasing the rear index by 1. What does that mean? Well, imagine the rear reaches the end of the queue. Instead of stopping there, it magically appears at the start of the queue. It's like a loop that keeps the queue going in a circle. Now, we know where to add the new element because rear pointers to the correct position. So we simply place the new element in the position pointed by rear. DQ operation. First, we need to check if the queue is empty before removing an element. We don't want to remove something that's not there, right? That's not possible. So when we remove an element, we return the value pointed to by front. That's the element we want to take out of the queue. And now comes the exciting part. We circularly increase the front index by 1. Just like we did with rear pointer, when the front pointer reaches the end of the queue, it magically appears at the start. Remember, our queue is like a circle. But there's a special case when we need to watch out for. When front pointer reaches 0 and rear pointer is equal to size minus 1, or when front pointer is just 1 less than rear, that means our queue is full. So we need to handle this case carefully. Lastly, if we remove the element from the queue, we reset the values of front and rear to -1. This indicates that the queue is now empty and ready to be used again from the beginning. And there you have it. That's how the DQ operation works in a circular queue. It's pretty cool, right? So the circular queue increments make it so efficient and allows us to make the most out of our queue's memory space. Now, let's dive into the complexity of NQ and DQ operations of a circular queue when we implement it using arrays. You will be happy to know that the complexities of both NQ and DQ operations is quite efficient. We can perform these operations in constant time, represented by big O of 1. This means that the time taken to NQ or DQ an element does not depend on the number of elements in the queue. It's always the same, making it fast and efficient way to manage our data. Now, let's explore some real-world applications of the circular queue. You will be amazed to see how versatile this data structure is. One significant application of the circular queue is in CPU scheduling. In computer systems, the CPU has to manage multiple processes that need to be executed at once, right? So, the circular queue helps in efficiently scheduling these processes, ensuring that each one gets its fair share of CPU time. Another important area where the circular queue shines is memory management. In computer systems, memory is a precious resource and the circular queue plays a crucial role in managing it. It helps in organizing and allocating memory to different processes, making the best use of available space. Lastly, the circular queue is also employed in traffic management systems. In scenarios like traffic signals, where vehicles need to wait in a queue before crossing an intersection, the circular queue ensures a smooth and fair flow of vehicles, preventing congestions and ensuring safety. So, you can see how the circular queue is an essential tool in various domains, right? Making our systems more efficient and organized. So, keep exploring and applying your knowledge and you will see the incredible impact of data structures like the circular queues in the world of computing.